Okay, welcome to this explainer. Today, we're diving into a genuinely groundbreaking framework called SpikMamba. We're going to explore exactly how this model is completely changing the way AI processes high-speed temporal data. We're talking about a massive breakthrough at the intersection of bio-inspired cameras, spiking neural networks, and a revolutionary architecture known as Mamba. Together, they're unlocking a whole new era of privacy-preserving human action recognition. So imagine an AI that sees time exactly like the human eye does, without recording a single actual picture. Think about your own biological nervous system for a second. Your eyes don't process the world in a continuous stream of dense, high-resolution photographs, right? Instead, your retinal neurons fire only when there's a stimulus, like a sudden change in light or motion. While event cameras operate on this exact same bio-inspired principle, they literally don't take pictures. They only record changes. We've got a great roadmap to guide us through this complex architecture today. We'll start with the event camera challenge, navigate the temporal data dilemma, unpack the SpikMamba framework itself, look deeply at how it models time locally and globally, and finally wrap up with some stunning benchmark results. Let's kick things off with Section 1, the event camera challenge. We're facing a really fascinating paradox in modern computer vision right now. Think about standard RGB cameras. Sure, they give us beautiful, dense frames, but they suffer from terrible motion blur at high speeds. And, critically, they record facial textures and identifiable features, which creates massive privacy risks. On the flip side, we have event cameras. These give us incredible high dynamic range and are inherently privacy-preserving because they just don't capture full textures. The catch? They produce a hyper-fast, spatially sparse stream of data that is notoriously difficult for traditional AI to actually process. Mathematically, the way we represent this data is super interesting. An event is literally only triggered when the brightness, or log intensity, exceeds a specific predefined threshold. When that happens, the camera just spits out a simple data point, X for the pixel location, T for the exact microsecond timestamp, and P for the polarity, meaning did the light get brighter or darker. By only triggering on these changes, the camera completely eliminates all that redundant background data. Like if you're standing perfectly still in a room, the camera essentially sees nothing. It only sees your movement. And that brings us to Section 2, the temporal data dilemma. Here's the problem. This hyperfast data creates a massive computational roadblock because our traditional methods are fundamentally flawed for this specific type of data. Current artificial neural networks, or ANNs, just can't handle that microsecond temporal resolution. So to cope, they downsample the data into chunks. But you know what happens when you downsample? You lose the micromovements, all those fine-grained temporal details of a human action. Now, on the other hand, we have spiking neural networks, or SNNs. These are highly efficient because they use binary spikes, literally just ones and zeros, which perfectly match the event camera output. But SNNs get trapped in short time windows, so while they capture the micro details efficiently, they totally lose the overall global context of the human action over time. So the million-dollar question for AI researchers was this: how do we capture global time without losing SNN efficiency? Basically, how do we see both the forest and the trees at the exact same time without melting our computer's processor? Which brings us perfectly to Section 3, introducing SpikMamba. Mamba is absolutely the secret sauce here. It's what's known as a selective state space model. You see, in traditional AI architectures like transformers, processing long sequences of time takes an enormous amount of memory, what we call quadratic memory complexity. It just gets exponentially harder the longer the video is. Mamba steps in and replaces that with linear time selective recurrence. It takes continuous state space equations and converts them into a discrete form. This allows Mamba to handle long sequences of time dynamically based on the input, all without needing massive computational power or huge memory footprints. All right, moving on to Section 4, local versus global timing. Under the hood, this pipeline works in a brilliant three-step process to synthesize both micro and macro timelines into one coherent output. First, something called spiking 3D patch embedding takes the raw event frames and projects them into spike form features. Once the data is in the spike format, it passes through two highly specialized layers, SpikSLA for processing the local time and SpikMamba for the global time. Let's look at step 2. The SpikSLA mechanism zooms right in on those micro movements. SLA stands for spiking window-based linear attention. It reshapes the data to isolate specific temporal windows. Using spike form queries and keys, Again, just simple binary data to capture local action details without wasting energy. This guarantees that the rapid, subtle movements picked up by the event camera aren't just smoothed over or completely lost. Then, the SpikMamba layer zooms out. Think of this layer as the global conductor. It takes those localized spike features, expands their dimensions, and feeds them through Mamba's discretized continuous equations. By applying what's called a Hadamard product, which is basically an element-wise multiplication with the local data, it pieces those local spikes together over the entire 5 to 7 second action sequence. This is exactly how the model understands that a rapid series of local twitches actually represents someone throwing a ball or waving their hand. And we know both steps are absolutely crucial because of ablation studies. When researchers completely removed the local spikelet SLA layer and only relied on the global Mamba layer, they saw a massive 19.73% average drop in accuracy across their datasets. It turns out you simply cannot understand human action without capturing both the micro movements and the macro context.
Let's hit our final section. Efficiency meets accuracy.
The sheer scale of this victory is honestly staggering. Take a look at the comparison between SpikMamba and Exact, which is a state-of-the-art but power-hungry artificial neural network. On the hard-vase dataset, which is a massive, highly complex dataset for human activity, SpikMamba jumps over 7%, going from 90.10% all the way to 97.32%. Across the board, SpikMamba doesn't just beat previous spiking neural networks, it absolutely shatters the records of standard continuous value ANNs on these event-based datasets. But here's the real kicker. SpikMamba achieves this state-of-the-art accuracy while using practically zero power. If we look at the G-flops, which is how we measure computational complexity, SpikMamba operates at just 0.12 G-flops. Compare that to Exact at 1.1 G-flops. SpikMamba pulls this off using only 0.18 million parameters. It's a tiny, tiny fraction of the computation and memory footprint that previous models required. This whole architecture is a massive paradigm shift. By eliminating key value caching and using that linear time selective recurrence, the memory footprint shrinks dramatically. And this massive efficiency gain means we don't need huge, expensive cloud servers to run this AI anymore. We can now deploy high-perception, privacy-preserving human action recognition directly onto small edge devices, mobile robots, and neuromorphic IoT architectures right in our homes and cities. So, I'll leave you with this final fascinating thought to wrap up our explainer on the incredible potential of merging spiking neural networks with Mamba. We've just proven that we can model highly complex temporal data at the absolute edge of computing with minimal power, all while totally preserving human privacy. If our devices can understand exactly what we are doing without ever actually seeing who we are, we're looking at a fundamentally safer, smarter technological future. Something to think about until next time.